it's my great pleasure and honor to actually invite or to introduce Professor Ling Guan from the Electrical and Computer Engineering Group at Ryerson in Canada, Toronto. He's published extensively on multimedia processing and communications and human-centered computing. And I hope you'll forgive me for reading a bit this because he has a certain number of awards and I just want to mention them and I don't remember them all. So he's a fellow of the IEEE, a elected member of the Canadian Academy of Engineering, and he has many awards, and he has the Canadian IEEE Gottlieb Medal for Achievement in Computer Science and Engineering. And today he's going to talk to us about the advance of sensory computing technology, particularly in sensor fusion and the complexity of sensor fusion, and he's worked on a new technique to look at sensor fusion. And he's going to explain to us this new technique in his talk today. So welcome, please, Professor Guan.
Okay, thank you very much for the chair. I think first you'll notice the difference between my affiliation. Okay, when we submitted, we were still called Ryerson University, but now we are Toronto Metropolitan University. But anyway, for some reason, okay. But anyway, so this is a work for my postdoc, Dr. Li Gao. Do you have a pointer or no pointer, right?
No, there's no pointer.
Okay, all right, that's okay. So first, I really say that I really enjoy your country. It's a very beautiful country. I would term it paradise on earth, okay? Anyway, so the title of this work is a deep discriminant fractional-order canonical correlation analysis for information fusion. Sorry, okay. So here's what I'm going to, I'll try to be slow because I prepared to 25 minutes. I didn't realize I got 35 minutes. The same length of time as the keynote speech, okay? Anyway, so it's really equal word here, okay? Anyway, so first very briefly about background, motivation, and then the proposed method, and experimental result and analysis. And actually, I thought I can replace these slides. So actually, I add a few slides to somehow explain why such architecture in general works, but I seem I can't do it, but I will just very briefly tell you why such architecture, works. The architecture is actually against the deep. It's in my opinion, it's not deep, but the student call it deep, so I just keep that and also make it easier to get accepted. Okay. Anyway. So information fusion, essentially work on information fusion. Essentially, we work on the mathematical and statistically motivated information fusion. And then, but more recently, we merge this kind of statistical fusion with some kind of neural network architecture, okay? And this is one of them. So essentially, information fusion has been, because it's naturally our doing information fusion every day as a human, right? So it become quite important, and a lot of people have been working on this recently. The one of the classes, what we termed as a mathematics-inspired method. In that method, the class based on canonical correlation analysis has shown that its power. So there are some of the methods which are relevant to this research are listed here. Kernel CCA and deep CCA, deep and discriminated CCA, and multi-wheel fraction, deep CCA. Okay? Probably I should come here. Actually, I have my pointer, but it's left with my wife outside. Anyway, I thought you should have this, okay? So, but anyway, and then the multi-wheel fractional deep CCA. The multi-wheel is what I'm interested in, because normally when we talk about canonical correlation analysis, we talk about two streams, two wheel. But you have more than two wheels. Okay, at least you have audio, visual, and you have the smile and touch, etc. So it should be multi-wheel. Okay, and even with single wheel, let's say just speech. What you say doesn't count too much. What actually your intonation, that kind of information actually count more. So for speech, at least you have two streams, vocal and phonetical, right? And for visual, that's even more true. You have RGB, you have depth, this kind of information. So even you're thinking about the data from one kind of sensor, let's say visual sensor, actually is a different visual sensor. So that's why it is really kind of important here. You have to think about the multi-view, all right? Not just two-view, multi-view. So the state of art, related to my research is the discriminant correlation analysis. The key word here is discriminate, because you just do CCA, there's no discrimination. Okay, if you are familiar with this kind of method, you have to introduce this kind of discriminative information so that it can better process this multi-view data. But when you do this, the challenge is very interesting. The sample-based matrix, because anyway we use samples, right? It's a data-driven. Okay, the matrix are unbiased estimate, but the agent values are biased estimate. So this actually makes some kind of inconsistency. How do you actually try to deal with this kind of discrepancy here? Okay, so a potential solution is a fractional order algorithm. So because some ongoing research shows that if you're integrating statistics guided optimization, that's we actually name that. It's essentially is a machine. Or you can call it a statistical machine learning kind of method, okay? With neural network architecture. So that kind of architecture exhibits model agnostic properties and is ideal for interpretable machine learning. We have quite a number of models, but this is the model I'm going to talk about here, okay? So if you see that there is a deep discriminant fractional order canonical correlation analysis method, that's what we proposed this time by integrating the architectural neural network with the fractional order CCA. Okay, so the function of the fractional order is try to make your estimation of agent value as accurate as possible, because that's the problem with the general method. Okay, and in the correlation method, and then construct the FO discriminant correlation matrices. So essentially, you can see that it's based on this agent value, so that the matrix would make sense. Okay, so hence, so that we expect that this kind of architecture can generate high quality information representation and interpretable model by using FO and neural network architecture, and to actually combine them together to use to form this SGO and strategy. Here are some. I had to be apologize because there are a lot of mathematics. Okay, here. Okay, but they are actually quite simple. The start is that you have two random variables, and then but they are biased. You try to remove the bias to find the mean, and then you have the unbiased. The vectors. Okay. And then there are two important matrices here, correlation matrices. One is within class, or sometimes we call it intra-correlation class, a matrix. And between class, sometimes we call inter-correlation class, okay? So, and then you form this kind of correlation matrix, and the objective of this DCA is to try to find the projected matrix WX and WY, so that you can you try to minimize the values which are in the same class, and to maximize the values which are in different classes. Okay, this is normally what we do in pattern recognition. Okay, essential solution is I think most of you are familiar with. Use Lagrange multiplier and agent value decomposition. This is very classical. But that's a classical one. But if you want to do that, to introduce the kind of neural network, you essentially introduce some nonlinear. This function, okay? You try to introduce some kind of nonlinear function here. The G are actually realized by neural network, right? As you will see. And of course, they can be written in the vector form, okay? So then in the vector form, that's the format given here, okay? And then, up to now, it's the background. Now is what we did. So what we did, if you go back to here, here, there's no fractional. This is a, kind of full kind of representation. But here, if you have this kind of alpha, so that you don't use 100%, you use a fractional of this correlation here. So, and then you from the fx, fy, in the previous slides, you get this kind of solve this kind of problem. Even in this case, you solve this problem, the orthogonality constraint is imposed so that it becomes this. You try to optimize this one and subject to these two equations. So essentially, this should be orthogonal, which means that it should be equal to identity matrix. Okay, so then you follow this procedure. You are actually to solve that one is essentially to try to find the trace. Okay. How do you find them? Sorry. This differentiation to find the 0, and then you got this value, and this will give you the two mathematical expressions for the solution. As I said, that G function is actually realized by neural network. So by this kind of neural network. From here, I can already tell you the network will never go beyond the 3 layers. I have a reason why we don't need over 3 layers. Okay? But anyway, here you have data in here. You use this to process it, and then you get into the fractional order, and then you get the. This is not the result, not recognition, but the representation. And then you use whatever classifier you want to use to work on this, in a sense, optimized feature. Okay. We have a few examples here to show. This is another thing here. You can see here, we have some this one, it has about 60,000 samples. It's not very large, but it's okay, right? For this one, it's very small, only 600, okay? And for this one, it's a Cortex 101. It's about over 10,000, but it's 101 classes. That's a lot of classes, okay? So, so you can see here, what I want to show here is that this kind of method, not just this method, this kind of method, when you use correlation analysis, it can deal with both small sample data and large sample data. And in the same time, it can deal with different kind of features, from pixel to output for real deep learning networks, as I will show you here, okay? The first one, the handwritten, you can see that is 60,000 training samples and 10,000 testing samples. We also, use 10,000 samples for tuning. We normalize them, and it's very interesting. The two wheel here is just the left and right. Okay, so which sometimes sometimes I can't explain, but it's very interesting. You split your data into two, however you want to split, and then you use them. You put them together. You get something really good. So here is a very simple kind of way, right half and left half. I'm not one, invent this. All this kind of method, use this. Somebody said you can do that, okay? We just say, okay, let's see if we can do better based on your data setup. Okay, so this is what the result. So the result looks good, at least when you compare with those methods. The second one is for emotion recognition, but only audio emotion. This is what I said, that you can do that even for the speech. You can do fusion, or information fusion. This is this emotional database is our small database. We came up with this database, and it has been somehow accepted by the community. So you can see that the sample is very small, only 655 samples. And if you just if you use individually for prosodic and MFCC, that's the kind of performance you get. But if you use that architecture and then you can see here, that's what we got. Again, we didn't come up with that feature, but of course this time the feature makes more sense, okay? Because one wheel is vocal, another wheel is phonetic, so it makes more sense. But anyway, what I want to show you here is that it's a 3-layer cascade network, only in the 3 layer. We don't need a very really deep neural network to do that. And then this is probably the most difficult one. This is a Cortex 101. It has 101 classes, and this how this kind of image is kind of arranged. And you can see the output. Input is again very interesting. This, if you do deep learning, you know what does this mean, right? FC6, FC7 is just mean the 2 output layers. Okay, after you finish your feature extraction, use deep learning, and then you use a full connected network, layer 6, layer 7. We just use that as the input. Here is one thing I think that's my understanding why you can do this. If you are familiar with wavelet, you use wavelet, you decompose wavelet, and then you put them together. Essentially, each band of wavelet represents a different kind of information in terms of strength and the kind of scale, right? Here, I think that here's what actually similarly happened here. Oh, okay, thanks. I'm finished. Okay, almost finished. What happened here? F6 and F7, they actually represent information in different kind of levels, okay? Different kind of scales. So if you put them together, you can see that, that's the result we got here. I don't want to blab too much because maybe somebody say we got something better. Okay, that's what we compared. What I want to draw your attention is still here. It's a 3-layer network. That's sufficient. Okay, so before I finish summary, I still got a couple of minutes. Yeah. I just want to say in general why this kind of network works. Very shallow network. I really wouldn't like to call it deep. The only way, what I argued with my postdoc, he said, why? Because the 3 layers are CNN. Okay, still CNN. I said, okay, let's keep that. But there is a theory. The theory actually was in the 60s by a Russian mathematician, Kolmogorov. He has proved 3-layer neural network can do anything. Why we can't do it? It's simply because then we didn't have the kind of, we don't know how big that should be. We don't know the exact design. So that's a problem. But then in 2021, there was a paper actually, more clearly showing why this kind of network works. And we actually use this kind of network, particularly in terms of the multi-wheel information fusion. We actually show that with several different kind of model, it works. Okay, so we actually you have a code upload, not this one because this one is too new. We have a code upload there. Okay, but anyway, I'll stop here. We propose this network. We incorporate it into NN-based architecture. And so it generates high-quality representation of feature fusion. So the experiment result I showed you, show that it works as far as the comparison. Okay, so thank you very much.
Thank you. Thank you for this talk. Do we have any questions? Please.
Okay, thank you very much for the talk. I have a question. If I understand correctly, here the method applies to the single modality, either it's images or audio data. multimodality, say emotion recognition?
Yes, of course you can, and we actually have that kind of result. But when I start, I'm an image processing guy. I start with image processing, and this because we didn't have time to do too many experiments yet. All this kind of method, this CCA-based method, can apply to multimodal. What I call here, the 3 examples, yes, I think you are very sharp eyes because it's easy to implement. A single model but multiple feature is a special case of multimodal. You could see that.
Okay, so basically this model can be directly applied to different modalities.
Yes. If you want to try my other model, I think it's a much mature model. I can give you the link. You can try that one. That one, essentially, we don't have any kind of constraint. What kind of data you can use in the processing? You can do that in many, in any, as long as you have 2 or 3 or 4 streams of data or features.
So maybe one question.
Please.
So in this case, I expect the result, the fusion information into a neural network to do, for example, emotion recognition.
Yeah.
More accurate. Is that true? How the model runs in terms of speed?
Speed, you mean?
Compared to if I just simply concatenate these feature vectors.
Well, you just concatenate. Yes, of course. If you just concatenate feature vector, it will be fast, right? But that's the most primitive kind of fusion method. That's, you can feature level fusion, representation level fusion, and then you have score and decision level fusion. I can't say representation level fusion is better than score level fusion, but I can say definitely it's better than the feature level fusion. Normally that's the case. Okay.
Yeah, thanks.
Okay.
Thank you. Yes, please.
Thank you very much for the presentation. I had a question about alpha, the fractional parameter. What cannot you kind of model with these whole covariance metrics that you can model with the fractional parameter alpha?
Yeah, so for this one, we haven't got a very good kind of automatic way yet. Essentially, it's a try and error for now. Okay, yeah.
Are there any other questions? If not, I have just a quick question.
Sure.
So I'm just curious, is there an indicator that you can use when you use data fusion if you lose information when you do it? So how do we measure the data that gets lost because we have to fuse the data? Does it make sense?
Well, this is why I like this one, like the representation level, first of all.
Mm-hmm.
For feature level, you could have a lot of data. That's why when CNN first come, they just use the pixel, let's say, for image, right? But then they said, no, we can't do that. Yes, you have full information until last stop. But how do you process them, right? But if you go to the let's say, the score level, we only have a few numbers.
Mm-hmm.
So that's why we think if you can, at representation level, you can find a good representation. Then you still keep most of the information while you reduce the data a lot.
Mm-hmm.
So that's why we believe that the CCA family is a good tool to do that, because essentially you are doing a mathematical projection or mathematical transformation, right?
Mm-hmm.
It's just like PCA, but PCA only deal with one stream of data, but here you can deal with multiple streams.
You have very nice results. Thank you
Thank
very
you
much,
very much.
Professor Guan.
Thank you very much.
Thank you. Thank you very much.
Thank you.
You're welcome.